Good afternoon. Can anybody hear me? Yes. So I'm going to do a quiz number 3A to see what is your answer. So we did the 5.20. So quiz number 3A answer. So how can I add a poll save? No? Let me see what I'm doing. Launch the poll. Okay. So please give me your answer of your last quiz about your okay. We still need more. $38 of 50 voted. I need more. Okay. I see still students are logging, and 51. So it looks like we only have 51. We have 10 people didn't show up or didn't answer. I have 52. Yeah, everybody is here. So, okay, good. Yeah, 52. I got 53 or 52. We only have 9 students didn't show up today. But after thinking about it today, I think, okay, don't tell people all the answers. So I'm going to end the poll, okay? And we'll share results. Okay. I shared the results. Did you see the results? 80% of you said that is 0.25 because 0.5 times 0.5 is 0.25, which is unfortunately wrong. The reason you are wrong is because you forgot the circuits, or you forgot the correct answer is 0.20, okay, not 0.25. Strange or not? Okay, so it's not strange. Let me tell you. So I'm going to solve your. I already shared it. So what are you saying? Chat. Can we go through it? Yeah, I'm going to do it now. Yeah, yes. So, okay. So let me see. I'm going to show my video panel. I'm going to hide my floating meeting controls. So great. Are you ready? So first of all, let me tell you that 0.5, you have input, you have output, you have input, you have output. So you put this together. Ideally, is 0.25. Ideally, right? But in our case, it's not true. The reason is we forgot there's one thing, it's called output impedance. We forgot to talk about here as an input impedance. They are not matched. So therefore, you cannot directly, so this is wrong in this case, okay? So why? Why in this case is it's very simple here. So you have, this is R, this is R. So you have here, right? So you have another one. So you have R in here, you have another R in here. And pull out, this one is a V4, right? So this is V1, this is V1, this is V2, this is V3. So you just pull out these two together, okay? So in this case, we want to know what is the V4 divided by V1, right? I'm telling you that this is 0.2. Do you feel surprised? Let's start. So let's assume that we have a current flowing in this branch, that's I, right? So the voltage in here, V4 is I times R. Do you agree? No problem. So of course, this is also I. So this is also I times R. So in here, what is the current? Oh, so what is the V3? What is V3 from here to here? V3 is, of course, 2R, so R plus R, okay? 2R times I, right? Right? Yeah. So because V3 is 2R, V3 equals V2, right? V3 equals V2. Is V2. So V2 is also 2R times I. So this voltage is 2R times, so what is the current in here? In this R? This is 2I, right? So this is 2I. So remember, you have an I in here. This is I, right? So this is I. Then you have 2I in here. What is current in here? 3I, right? 3I. So you have 3I times R. You have a 2I times R. So the total voltage from here, the V1, it is 3I times R and 2I times R. So V1 is 5R times I, right? So this is basically V4 is I times R is this one, okay? So divided by what? Divided by this one, 5 times I. So this is 1/5, this is 0.20, right? So what happened? What happened? What we missed? Why 0.20? Why this is wrong? Okay. Then how to make it correct? How to make it correct? So that means you need something called impedance matching. So the output impedance here is not, output impedance here is not what? It's not 0. Input impedance is not infinity. So they have problems. They have problems. So for any of the signal, when I say any signal, okay, it is an output of something. It has a mother to generate that signal, right? So we usually call this is the generate the signal. That's the signal S of t, right? So this is S of t. So this is my signal, all right? I'm generating a signal, S of t. But remember, we ignored this R in here. We ignored it. We assume this is 0. So when I have a signal here, when I have a signal in here, this is a signal, right? So this can be look from this side in, you guys have learned what? Thevenin's equivalent stuff. So then in this case, R is not 0, okay? It's not 0. All right, R is not 0. So therefore, so output impedance and input impedance, they are not matched, okay? Not matched. Okay. So that's called load effect. Load effect. Okay. So let me just give you another idea here. So you have a signal. So you have a V1 signal. You have V1 signal. Okay. You get this V1 maybe from somewhere signal generator. Okay. Okay. So this is a signal from R. This is a signal. Okay. Okay. So you pull out this one and connect it. Then you put this R, then let's say I want to do a voltage divider. Okay, this is a voltage divider. I pull out this one. This is my V2, okay? So I didn't put RL, this is load. So this is a kind of load, okay? Kind of load, or next stage of my circuit. So ideally, this RL should be as big as possible. Otherwise, it will drop. Okay, you will have some current growing, then V2 will drop. Okay, so this is like you treat this one as this first stage. You have this second stage. Okay, usually this is the signal source. This is load. Okay, this is load. So from load side, you have input impedance. From source side, you have output impedance, right? Output impedance. So this ideally this should be 0. Ideally this should be infinity. Then you don't need to worry about loss of those efficiency. Okay. Okay. So as you are going to learn today, usually we need a stage of op amps in here. This op amp. So that when I put in that op amp, okay, this will be true again. Because in the op amp, ideally, this is very small. This is very big. Okay, so you don't have that worry at all. So today, if you do the quiz, I'm pretty sure you understand what I mean. What's your answer? So with this, any question? What was missed is called input-output impedance matching. Okay. So if you check our textbook, I have a textbook in front of me here. So this is our textbook. Okay, I have a textbook in here. Can you write down a magic number you are going to read after the class? So it is page 234. Page 234. Okay, section 4.2.2, impedance matching. Okay, so the impedance matching is not only a useful concept for electrical circuits, it's actually generally applicable to other circuits, mechanic circuits, hydraulic circuits, thermal circuits. Okay. All right. So today we are going to learn op amp with the question like why op amps will solve this problem. We'll never get to this trap. So don't feel shy. It's good motivation for us to study op amps today. Okay. Questions? Questions? Do you have questions? type in the chat box. I'm monitoring. Okay. Oh, do you expect us to get this quiz wrong in order to lead to the lecture? Yeah, of course. This is my designed trap for you. It's on purpose, actually. Yeah. I know most of you will get it wrong. So I know. So this is my traditional trick to motivate you to learn op-amps. But there are more things about op-amps, okay? So think about, now, actually, I'm not going to, if you do quiz wrong, I'm not going to give you a 0. If you submit, you get, it's for the attendance. But if you submit a quiz is blank, that I'll treat it as you missed the class, okay? Don't fool me, please. Do it, force you to learn, okay? So don't worry about you do it wrong. It's okay, but you have to do, okay? So, excellent. So, okay, so today we are going to go through the op-amps. I hope you now, maybe you heard about it or even you played with it. So we are learning this one from different perspectives. So with that, we are going to learn also signals and systems, okay? So let's get started. I call this is op-amp module. So we are going to spend next week and next week. So sorry, this week and next week, we're going to cover the op-amps. So all right, so let's move on. What's the problem here? Do you see this clearly? So op means operational, right? Operational. Why we use this one? I told you we have if we are elementary school kid, we know operations are summation, multiplication, division, and subtraction, right? So, but if you are a high schooler or college students, you should know other operations like differentiation, integration, right? So first of all, I showed you that the impedance matching is an important concept we probably missed, but it's okay. Let's learn it. But in the real world, op-amps is everywhere. In your iPhone, do you have op-amp? Of course you have, because otherwise you cannot put your speaker you can hear it loudly. So that's, you have an audio. Yeah, you also got stereo in the car, yeah. So you work with amplifiers every day, so amplifiers, audio amplifiers, power amplifiers, okay? Because some of those signals are not strong enough to drive something, right? So you need to amplify it. So like motors, okay? And so on and so forth. And you got a Wi-Fi repeater, you heard about this. So you need amplification of your Wi-Fi signal. And drones, of course. Do you guys do an intelligent guess? What's this? RTF. Ready to fly. Okay, you can buy a drone ready to fly, you know. So for a motor, to make the motor turn, those control signal is too weak. You have to amplify it. Okay. So this is called servo amplifier. So you have this this amplifier to make it a high power, like how many watts. Okay, the motor could be very big. So the amplifier inside. So basically, we are going to learn something here regarding the servo motor. because it's AC, so you need a switching circuit. You got a logic, you got a feeling. This is a transistor, this is a transistor, this is also a transistor, this is also a transistor, this is a diode. This is what? Do you guys know? Oh yeah, you said it here. Transformer, I'm sorry. Transformer. You have two sides, okay? You have coils one side and the coil, yeah. Not inductance, yeah. Yeah, not inductor. So this is a capacitor. So this is what? What is a POT, by the way? So we usually call it a pot. So potentiometer, okay? Potentiometer. So it's a adjustable resistors and so on and so forth, okay? So there is a difference between a capacitor. Usually you do this or you do this, okay? There's a difference. Do you guys know what is the difference? Yeah, there's a polarity, okay? There's a polarity. So, so be careful, okay? Anyway, so, but there are more applications like antenna. Usually the signal you receive from the antenna is very weak. Then you need to amplify it, right? So the GPS and so on and so forth. So it's everywhere. Basically, also like you heard about WII. So you basically to make the accelerometer signals amplified, you get motion signal. And the temperature sensors is so weak, you have to amplify it. So speed sensor, location sensor, GPS, okay. Yeah, if you blow the tube, the police ask you to blow, you should. Don't refuse, okay. So alcohol sensor. So it's also a very weak signal. Then you amplify, then you will visualize it and convert to into the display, see whether you are over the concentration. Of course, this is also useful for heartbeat. Okay. So when you pick up the signal from your fingertip, it's actually very weak. So you need to amplify it. Okay. So so all these are we need amplification. What does that mean? So it is needed everywhere. Okay. So we really need to study some of the amplifiers' basic principle. But we're not learning the amplifiers from circuits point of view. We're learning it from system point of view. Okay. System point of view, basically, we need to define what? Something input, something output. Okay. This is abstract. Sometimes people say, oh, where's the ground? So yeah, you can say, oh, you put a ground in here. Or you put a ground in here. Okay. But usually we drop that. Okay. So for the amplifiers, and we are going to talk about, I said input impedance, but actually, and let's start from simple. Impedance is a complex number. Resistance is a real number. Let's talk about resistance, okay? That means the things that we're talking is resistive, okay? Resistive. It could be capacitive, could be inductive, okay? So this is clear. You have, say, this is a ground, okay? So you have an input, you get output. So usually you have output, but you need to hook up the output. So basically there are three stages I can see. Stage one is a signal source. Stage two is amplification. Stage three is your load. You need to amplify the signal to do something like put a speaker in here. Louder speaker, right? Loudspeaker. Okay. So originally you have signal source, amplified, So then basically it's A sub V, okay? It's amplification of the voltage. There's a voltage amplifier. Sometimes it's a current amplifier. So this kind of thing is straightforward, right? So in the future, I hope you look this thing into a system point of view. So from my point of view here, so this is the source, okay? Like in the Simulink, you have a signal coming from a signal source generator. While the generator doesn't have other input, that's just generating your signal. It's called source. Like it's a step, sinusoid, all those are sources, okay? There's a family of different sources, okay, in the Simulink. But on the other hand, you need to add a signal, plug into something, eventually you put it into scope to take a look. That scope is all load, so it's like sync. Just go there without going anywhere else, okay? There's a signal coming in and coming out and stay there. So that's why in Simulink, you have two categories of signals. One is called source signal. Another one is called sinks. So like oscilloscope, LED display, and so on and so forth. All these things will signal come in without coming out. So that's called sync. Get it? So now we put everything pieced together. This is a real world application scenario. You have signal source, then you have a load. So we are going to talk about in the ideal op-amp case, what does that mean? And in negative feedback, what does that mean? Okay. So when we say we have an amplifier and the ratio is the input and output, if the output is inverted, we call this inverted. So inverting. So the phase is upside down, okay? But the amplitude is different, okay? So then we call this is a gain. So this actually, this parameter, this AV here, is called gain. But you may argue with me why we don't call it loss. It's okay, you can say this is loss. But traditionally we use gain, okay? So the question is, when gain greater than 1, we call this is amplification. Amplification. Tell me, if less than 1, what's this called? What's the term we call it? Type in the chat box if you could. 3, 2, 1. Type. Reduction is close. The in EE is actually is called attenuation. Amplification versus attenuation. ATT. Okay, attenuation. Okay. So it's not amplifying, but attenuated. Okay. So if offset sign is a negative sign, is called inverting, and then it's the same sign is called non-inverting. Okay. Inverting, non-inverting. Okay. So these are simple. There's something we need to talk about is a decibel. Have you guys know about dB? dB. Okay, dB. So a lot of people not familiar with the dB, but dB is so you have gain. It's used in the sound industry, yes. But especially when you have a gain, maybe the gain is very big, like tens of thousands. Okay. So, excuse me. So people keep forgetting what's original dB definition is the ratio of the input. So you have a system, you have input, but this is the signal. I can always say the signal has a power of in. It's a power of out, okay? Power of out. So then this dB here is the input and output, okay, input output. But so this is a V in and this is a V out, okay. But we say that A sub V is gain, okay, is a gain. But we didn't say that this is called signal gain. We didn't call it power gain. So this actually is a power gain, okay? This is a power gain. It's a 10 log 10 of power gain, okay? 10 log 10 power gain. But what if I have a signal gain? The V out by V in divided by V in. This is called signal gain. So this is actually AV, okay? Then you don't forget about 20 here. Because dB originally is talking about the energy ratio, okay? But well, where is this 20 come from? Okay, so remember, so if you have a resistor in here, this is R, so you have V, so going here you have I. So what's the power? Power is R I square or V square divided by R, right? So basically it's I times V, right? So this square, because of this square, will become this 20. So imagine, so P is proportional to V square, okay? So it's this is a V square, V out square divided by V in square, okay? It's bracket square without this square. So then this two will come inside. The outside is 2 times 10 is 20. So for power for the signal magnitude gain, which simply in the future called gain. If we say gain, we say signal gain, signal amplitude gain, okay? So that is, you need 20 log 10. So don't ask me in the future, why 20 log 10, not 10 log 10? So this is the reason. So don't forget, okay? So if you in a job interview, they say, oh, what is the dB definition? You tell them it's a 20 log 10, the gain. Then they'll ask you, what is 20? Why 20, not 10? You should explain this like this. Oh yeah, originally dB is defined as a 10 log 10 for the power ratio. The power is proportional to a signal square. Okay, either square here or square here. So that's why we have 20. I tell you, a lot of people don't know how to answer this question. Okay, be careful. Okay, let's move on. So it's extremely useful. Why? When you have amplifiers cascaded by another amplifiers, these amplifiers will multiply together. Okay, but the gain for the dB is just like turning like multiplication. So overall gain of multiplication of the individual gains, but if you do the dB, it becomes summation. So that will make life easier doing summation than doing multiplication. Make sense? That's why we need a dB. So you have a gain A1 times A2. So total gain is 20 log 10. So we're talking about signal gain, okay? A1, A2 are signal gain, not power gain, okay? So then it's just become a dB here, dB here. So this is dB, and this is another dB too. So just add together. But otherwise, you need to do A multiply A2, you know, A1 multiply A2. So clear? Now, let's talk about something linked to our arrow for the quiz 3A. Okay, so that's why explains 0.5 times 0.5 is not 0.25. So here is another angle to look at this problem. Okay, so you have a signal, then you always have RS. Okay, ideally RS is 0, but it's not usually. And ideally your load is open. So this is big, okay, but it is not, okay. So you have gain. So input terminal, you have signal. Output terminal, so this is just show you source, amplifier, and a load. Okay. So we take how these amplifiers work. Okay. So this is the most important part. Okay, most important part. Listen carefully. Okay, listen carefully. So I remind you that you have learned something called dependent source. Remember dependent sources like VC, VS, voltage controlled voltage source. You have VCIS, VCCS, voltage controlled current source. ICVS and IC. Oh, no, not IC. Why I do this? Current controlled voltage source and current controlled current source. So there are 4 different types. Okay, so these are called dependent sources. In our case, we are using a voltage controlled voltage source. So that is this guy. So this is a dependent source. You not a not a circle symbol. So this is called dependent source. So the voltage of this one is dependent on the voltage inside here. So this is V in is here. A is my amplification coefficient, the gain. Okay, the gain. And then I have R in. RS, R in, I have R in, okay, yeah. But of course, I hope R in is infinite, right? RS is 0, that would be nice. But let's live with this scenario. So then you have R out, this is called output impedance. So this RL is here. So we see how they play the input port amplifier act as the equivalent load with respect to the source. Output port acts as the equivalent source with respect to the load. So that's we abstractly look at the ideal amplifiers. Okay. So input R in is called input resistance, and the dependent source AV. This is dependent source. This dependent source is VCVS. Okay, so this is VCVS. Okay, voltage controlled voltage source. Circuit mode, voltage of the source depends on the voltage drop across R in. So A is called open loop gain. Okay, this gain could be made like 10 to the power of 5 or 10. So it's a very big number. Okay, very big number. And output resistance R out. Okay, output impedance, output resistance R out. So in series with this dependent source, the VCVS. Okay, so I hope this is not too difficult for you to accept. So let's assume everything is not 0. Okay, we just repeat in here. Doesn't this create distortion in the signal? Yeah, that's what I'm going to say. So, yeah, the answer is yes. So let's check. So from this side, this is the voltage divider versus the VS. So this R in, so this is a voltage divider, okay? It's a voltage divider of R and VS, V in. So this is no problem, right? So this is simple. So what we really want is a VL versus VS. This is my real, I want to check for the real amplification and how much, okay? So I care about that. However, from my output, I can see here, this is a VL. VL is you have 2 resistors. So you have a source. Source is this guy, it's a dependent source, A times V in. Then you have VL output. So this is a voltage divider again, voltage divider, okay? So clearly you can, no, sorry. Clearly you can put a V in here, V in here, okay? then we can establish this relationship, right? So this is what we are doing. So in the input side, output side, put together, you got this. So basically you have two output divider and A, okay? And A. So it is dependent not only on, of course, you dependent on how big is this one. So it's not only amplification side here, not only the A, but also this one and this one, okay? That means this guy as well as this guy are playing a role, okay? About my total equivalent amplification is here. Okay, this is my total. So, right? So that's too bad. And also dependent on the input output resistance, okay? And dependent on the source, depending on this RS as well. Okay, so different performance using different load source for same amplifier. So hopefully this is not true. That would be nice. So in other words, to reduce the effect, so R in should be very large. So R as ideally, so then R in is so that this V in here, this is V in will be same as VS if RS is very, no, sorry. If R in is very, very big, okay? R in. So this VL is simply AV in. So then that R out has to be very, very small, okay? So basically like open circuit, this is like short circuit. Okay, so that's why we need that. Otherwise, amplification is different. So in our case, our quiz case, the R in is 50% of the same. R in is the same size of RS, right? Okay, so that's no good. So let's see an example. Okay, so I have this non-ideal case. So everything is the same. This guy equals this guy, this guy equals this guy. Okay, so this all equal 50 ohm. And assume A is actually 50. So we try to find out what is VL divided by VS. Okay, so let's say we don't have this one. Don't have this one, then left-hand side is 0.5. Right-hand side without RL, then my VL, the VL is here, VL from here to here. This is open, okay? Okay. So it will be AV in is the same as this one, okay? There's no current flowing because this is broken. So this is, because I is 0 here, I is 0, okay? This is broken. So therefore, the current, the voltage is exactly the same as the source AV, and there's no voltage drop on R out. So it's 25 VS. So by doing that with RL, then you need to have another voltage loop. So it's a 12 VS. So the VS is the source, VL is the voltage. So you can see it's 25. This is another half. So, but A is 40. Oh no, A is sorry. A is 50. A is 50. So now you can see your 50 will become 25. Once you close the switching here, actually it will become another half. So that shows if you do not have a match idealized amplification, your amplification coefficient, you thought you can get 50, but actually you only get 12.5. So that should be alerting you that you should ask, what is my input impedance? What is my output impedance? Okay. Okay. So, so if I cascade these two, so I have another one is like this. So I cascade them. So then basically I have something like this. Okay. I cascade, I have two. So A is like a V in here. So this is another one. So I cascaded these two. So these are all 40. So instead of you have a 40 times 40 is 1600, you thought you are going to get this amplification. No, you end up actually it's only 200. Okay. So that means really we need something idealized. Okay. So we have this is, I think you can figure out. Okay, so there's another idea like I have a is 20, so I want this is a 40, so it's not enough. So how many of this you should cascade? So if you have two, probably yeah, it's 16. Yeah, so then you have n. Okay, how many stages? Okay, so then you solve n is 1.9, so you need to solve 2 stages. Okay, so this type of question is trivial. Okay, so just hinted you that in amplifiers you have a impedance, output impedance, output input impedance need to be taken into consideration when you do a multi-stage. Okay, so good news is people are using, so those are simple cases. So how to solve this problem? We invented integrated circuits. So this is the famous 741. Yeah, 741. So everybody in this field knows 741. It's a legendary design using discrete components. So these are discrete components. Okay, so these are very clever connections. You know, and these are 2 stages. Very so there's a very detailed analysis on this, but today I don't want you to zoom into this discrete components using transistors. You only remember this one is enough. Okay, so this is called integrated circuit, integrated amplifiers. Okay, so then you have eight terminals. Okay, so there's an inverting input, non-inverting input. So this is the symbol. So you have a power supply negative, power supply positive. NC stands for not connected. Okay, so we have no use. Okay, so the reason you have to do 8, you have 4 by 4, so you have 1 extra. Then those offset now and offset now is for you to adjust its drift. The amplifier may not be ideal, so you may drift. So these are the op-amp integrated circuit. So it's also called op-amp. In the future, we are going to refer to the op-amp integrated circuit instead of talking about this discrete components. Okay. So in fact, this is a well-known, well-patented circuit. It's much simpler to use using integrated circuits. Okay, so we are going to study all this 741. Okay, so with this type of circuits, how we can analyze everything. So we start by learning the idea of op-amp. What is the idea of op-amp? Okay, So you are going to see that this op-amp will solve our problem of impedance matching totally. Okay. So why we need to introduce negative feedback? Okay. So again, we're here, again, impedance. So what is the characteristic of our idea? So this is, this becomes our starting point, okay? This is our idealized operation amplifiers. So you have two terminals. This is called non-inverting. This is inverting. So you have voltage, the supply, to supply it. Because you need a voltage supply to make it work for you. So this type of op-amp is called active component. Okay, active component. While RLC will work for you without power supply. So then it's called passive. Okay, or passive. So when you have RLC, it's a passive without power supply and a bunch of them linked together, you're not going to make it blow up, okay? So it's always safe or stable. So therefore, there's a term, it's called passive. If you can make the system look like passive, then you don't worry about the system become exploded, okay? So in advanced controls, the passivity is actually a hot topic, okay? How you can design the overall system to behave like a passive system. So you don't need to worry about stability, blow up, explosion, smoking, that kind of thing, right? So just a side topic. It's connected. But now we have a active component in here. So physically speaking, okay, your V out, maximum possible V out is this guy. Minimum possible output is this guy, right? So yeah, true. So there is saturation limit. Saturation limit. And remember that this is the A. And we usually say the difference between here is epsilon, okay? And then the V out. So remember V out, I said, usually this is like plus or minus 15 watt is a power supply, or sometimes a plus or minus 12 watt, that kind of DC supply. So the V out is only like a 12. So this one equals A times epsilon. Okay. So let's say this is 15. Okay. Plus or minus is 15. Divided by A is epsilon. What if A is 10 to the power of 10? Because I said A could be really big. So then this epsilon is really small, right? Okay. Okay. So think about this. Okay. Think about this. And because of that, epsilon is so small, it's like a micro pico ampere. So small, so close to zero, 10 to the power of minus 10-ish. So you can imagine that even if you imagine there's some resistance here. So do you think, how big is this current? Your voltage is epsilon. Your current is voltage divided by this R, okay? And this R is not zero, okay? Even they're almost zero. So the I is also very, very small. So you get this one out. Is also very, very small. This I is very, very, very small. Do you agree? Yeah, it's very, very, very small. If you are in this is called open loop. Oh, it's open loop. On the other hand, so this and this can easily these are the signals from previous stage, okay? You hook up with this one. So this signal, if it is slight bigger than epsilon, it's very, very, very small. Say, for example, you touch it. Then this guy will suddenly become what? Saturated to 15 watt, okay? So this open loop is very sensitive to noise. You touch it, you saturate it, okay? So this is AVOL. OL means open loop, okay? This O stands open loop. OL stands open loop. So operational amplifier behaves much like ideal difference amplifier. Yes. So basically, you have V plus minus V minus times this very big number, you get a V out. But V out is maxed at 15 or 12. Okay. So this difference is if it is a little bit tiny bigger than certain tiny value, your output is stay there at 15 or minus 15, okay? No good. So it's so sensitive. If you touch it, you're saturated. Yeah. So of course, it is always true. This is always true. Always true. So you are going to see that this is a general amplifier model. We have studied it, okay? And about you have R in, you have R out. So, but op amp will also have R in and R out, okay? And AOL is very big, okay? Okay, so saturate means you hit to the maximum value, 15. I said that you cannot get something bigger than power supply here. You have power supply here, you cannot, that's your floor and ceiling. You cannot go beyond that. This is non-physical, okay? Non-physical. Okay, so we are now, this is like idealized textbook amplifier. Then this is start to become a real amplifier model, okay? We are using transistors, integrated circuits. This is the op-amp model, okay? But what deserves op-amp model is because of this guy is so big, okay? It's so big, what's going to happen? So in fact, because of that, we talk about ideal op-amp characteristics. So this guy is actually like broken, okay? Infinite input resistance. And you have 0, so this is like short circuit. I out is 0. And this A is infinite. So these are the 3 assumptions for idealized op-amp, okay? But if you say practically, this is like a very small, like very small value, like 10 to the power minus something. This is 0. No. So you should just have plus 8, 10 minus 5, that kind of range. Very small. This is like 8, 10 to the power 10, that value. Okay. So if you say R goes to infinity, that means no current flow into or out of this. So the current in here is 0. Okay. And also current in here is also 0. No, I was wrong. So no, we cannot say that. because depending on the load, you put it here, you put it here, you have load, you have current, okay? But ideally, so the V out is this, okay? Is AV in, so V out is AV in. The R in goes to infinity, okay? So no current go in or out of the any time. So these are I is 0 too, because it's broken, okay? So that's the ideal op-amp characteristics. But in reality, making the everything like this, of course, you can put like a VC. This is a VC minus. VCC is like a power supply. So ideally, we will never allow the op-amp used barely like this. This is called open loop configuration. Okay, so infinite open loop gain. So in other words, if you have anything non-zero here, non-zero here, you will immediately, because of A is infinity, immediately make this voltage hit to the maximum or minimum. Okay. So what about the effect of infinite open loop? That's if you have anything non-zero between V plus and V minus, then your output will be immediately saturated. Okay. Saturated means you hit your power supply, VCC. Okay. So usually we need to introduce a negative feedback. Okay, negative feedback. Say for example, I just link the inverting terminal to this one. Okay, so what's going to happen? So if I give you like this is like a 15 watt, this is like a minus 15 watt. So this is if I give anything here like 5 watt, and what is this one? It's also 5 watt. Why? This is because this is ideal as I show you. Why? Because V out is A minus A times this epsilon. Epsilon is difference between this. Okay, so V in minus V out. Okay. So I move A V out to this side. Then I'm going to get V out equals V in. Okay, equals V in. Then because A is so big, okay, so A is so big, so therefore V out equals V in is, okay, V out is V in. And because V out is V in, so this is actually 0. Okay, there's no difference in there. So it sounds either logic with some issue. No, don't question that. So you should say this A is very, very, very large. So the epsilon is so small, like 10 to the power of minus 10. Think that way, okay? Don't argue with me. 0 times infinity is 0 times infinity equals 5. Don't argue me this way. No. 0 times infinity can be anything, right? So, okay, so that's why I use epsilon, okay? Very, very small. So this is actually called a negative feedback configuration. And this is actually served as a voltage follower. So out and is in. So basically out and is in. So you remember, I have a 0.5 in here. So I want you to add op amp in here. Then you put 0.5 again here. Like voltage divider we did in quiz 3A. So quiz 3B is to put this guy in here, okay? Because in and out, here is 1, okay? Here is 1. Sorry, here is 1. This block is 1, okay? In and out is the same. V out, V equals V in. So in this case, this answer is, have peace of mind, please. It's this guy times this guy, it's 0.25, okay? Because of this amplifier, it will make your input impedance matched, okay? So we think about op-amp applications. So right now, we've gone through this, we explained that. So you can imagine that the system, after you applying this one here, your input impedance is infinity. Your output impedance is 0, okay? So therefore, you don't have that issue, the impedance matching issue. So sometimes this is also called buffer stage. I put a buffer stage here so that I don't have a worry about the impedance matching issue, like in our home. If it would direct connect, it is not 0.25, it's 0.20, remember? So that's why op-amp is so useful in practice. You insert op-amp, you don't need to worry about impedance matching issue anymore, okay? So this is called voltage follower, or we call a buffer stage to remove those potential impedance matching issue. Well, any questions? So your quiz, can you guys do your quiz today? And submit is easy, right? But I hope this week we'll learn an important lesson that when you connect two things together, you need to ask, can we really connect this? Do we have impedance matching issue? But if you have amplifiers, then you say, yeah, no problem. Because amplifier has that characteristics. Go back. Your input impedance is so big, your output impedance so small, okay? Therefore, no worry, okay? All right. So the rest is some entertainment, okay? So what are the applications? We have gone through quickly, but there are more. 741 is actually, we have learned this 8 pins. Model 741 is famous. So I have shown you this, okay? So those 8 points. So this, you have 8 terminals here. You have 8 terminals in here, corresponding numbers in here. So 4 is here. You have 3 is this offset now in here. Non-inverting input, inverting input. Okay. I'll go quickly, obviously, and we don't have time to go through all of them in details, but the op-amp 741 has a rich applications in real world by combining it with capacitor, diodes, resistor, whatever. Can be used as a timer, okay? Timer, okay, is very interesting. And you have timer. So like you press something here, you press something here, then the circuit will be on after a while. It's a timer, it's a delay, okay? Timer, you can also using, this is NPN transistor. So then this is your control input. And then you have a way to do ramp waveform, up and down, up and down. So using a very simple BJT. BJT stands for bipolar bijunction transistor, okay? And so basically you are charging this capacitor. So the analysis of these circuits are all possible, and if we spend time on it. And also there's a website, you can learn a lot of different circuits. But unfortunately, in your ME, in ENGR 065, you never put the transistors and the op amps and the capacitors, the resistors all together to study. So, which is okay. So you can pick up with those foundation knowledge. And you have optical receivers. Okay. Yeah, we can spend this for a while. So this is the 9-watt input, 9-watt input. So you have differential input in here. So you have a feedback. This is the feedback. This is another one. This is another one. So to me, this is integrator. So then that means if you have light, they will turn the light into a speaker. It will turn the sound. And active filters. We are going to cover active filters later, okay? Then this is dual power regulator. So now I'm not going to do that. So then radio receiver. This is even more. Let me show you one thing. Let me show you one thing. Do you guys know things that like this one? You know that you have this dial of your tuning your FM radio. That kind of analog radio, you tune it. So you get a different station, different frequency. Okay, so that's a radio circuits. So this is a jack you can plug into, can hear. So and these two are like transformers. Okay, transformers. And what's in between the coils? This coils is kind of like a ferromagnetic bar. Okay, so ferromagnetic bar. Okay, so to couple them. Okay, to couple them. So we see all these things are very confusing. You know, it looks very complicated. That hinted us to study carefully about op amp and its basic knowledge. Okay, so in the next 2 lectures next week, we're going to focus on that, and I'm going to show you that I said M, S, D, C, L, R. So all these things, they have op amp. You can build an op amp circuit to mimic this type of any type of system, thermal fluids. So in other words, all the system can be abstracted into ordinary differential equations. Okay, second order, first order, all in x dot is ax plus bu, y is cx. Okay, so that kind of what I'm saying is giving op amp, you can also do this as well. Okay. Okay. So op amps can be regarded as a building block for those differential equations. So from that perspective, because they can do a lot of operations, so of course they can do that. So from that point of view, this actually in the 60s is called using op amps, you can do computation. So therefore, it's called analog computer. Okay. So I do have an analog computer in my office. So too bad I cannot show you. I remember next time I show you a photo. Or maybe we have YouTube, I can show you analog computer. And in the 60s. So when you see computer is analog computer. Today, everybody using digital computer. But what if you say you have personal analog computer? Huh? At that time? Yeah, I also have one. That probably is very historic. So it's also in my office. I cannot show you. Personal analog computer. Maybe I can Google and find you something to show. So in other words, even if you only have a bunch of op amps, you can still do a lot of sophisticated things. So the first computer is analog computer made by the op amps to solve differential equations of ballistics of missiles. And, we can stop here. Sorry, a few minutes overdue. Any questions? You want to do the design, you have to start from the basics first. That's why our course is a foundational course. So don't miss the class. It's different when you attend synchronously. So let me see how many people here today. I have 47 here. That's not a good sign. I have fewer students. Yeah, everybody has a reason to miss the class, but you should overcome that. Please remind people to join the class. Use the time wisely. Don't miss class. Although I posted the recorded, that's not the same as synchronous version. We have lots of interactions in the chat box. You can see, right? So, all right. So I'm not happy. I only have 46 students. Well, but we do have quiz. All right. See you next week. Have a good weekend. Bye-bye. Bye. Take care.